In section 3.2, we're talking about two things, independent and mutually exclusive events. Now take note that these two things are not the same thing. Students try to make them the same thing, but they're completely different from each other. Now, independent events, if you got two of them, that means that one event does not affect the other one. So if we've got two dice and we're rolling them, if we roll one of them and it lands on a 2, we're not going to say that, okay, because it landed on a 2, that means when I roll this second dice, it's got to land on a 5 because the first one landed on a 2. We're not going to say that because they're separate from each other. Just because the first one landed on a 2 doesn't mean the second roll has to land on a 5. It can land on whatever it wants to. Now, the opposite of independent would, of course, be dependent. Dependent events, that would be where one does affect the other outcome or the other event. Now we got two words here, with replacement and without replacement. If we are talking about with replacement, that is always code word for independent events. And if we're talking about without replacement, that is always code word for dependent events. Now this says you're going to pick 4 cards, but you do not put any of the cards back. So that is saying without replacement, which is really just saying dependent. Because what you're doing is you start out with 52 cards, and then you take one of them out and you don't put it back in. So you went from 52 cards to 51 cards. So the probability of that second draw is going to be something over 51 and not 52. This one says you pick 4 cards and you put each of the cards back. So this one is with replacement, which that's going to be code word for independent. Now you've got your stack of 52 cards. You take one card out, you look at it, you put it back in. So you started with 52 cards and you ended with 52 cards. So the probability of that second draw is going to be something over 52. So it's kind of like a reset button because nothing really changed. Now mutually exclusive events, that are events that cannot happen at the same time. And when you look at events A and B, and if they don't share anything in common, or they don't have any shared outcomes, well, if there's nothing to be shared, then that would be 0. So it's the same thing as saying they don't share any outcomes, and they can't happen at the same time, so the probability of A and B would have to be 0. So if we look at this, we got a sample space going from 1 to 10. And then we've got our 3 events here, A, B, and C. So those are our subsets from our sample space set up here from 1 to 10. So what is a subset of A and B? So we're going to find the things that are common between A and B. So that's a 4 and a 5. So 4 and 5. Okay, so these share things that are common between the two. Mutually exclusive says they can't share things, okay, or they do not share outcomes. So since this one does, is A and B mutually exclusive? No, because they share outcomes. Now if we look at the subset of A and C, well, there's nothing shared between them. So is A and C mutually exclusive? Yes, because they don't share anything in common. Okay, we've got 2 fair coins. We're going to find the probability of each of these events. So F is the event of getting at most 1 tail, 0, or 1. First write the sample space. So we're flipping 2 coins. So 2 events here. The number of outcomes for the first flip would be heads or tails, so 2. And same thing for the second. So that means I should have 4 items or outcomes within my sample space. So it could be a head and then a head, or a head and then a tail, or a tail first and then a head, or both of them tails. Okay, now F is saying 0 or 1 tail. So 0 tails would be both heads. Head, head. and then one tail. So that could be head, tail, or tail, head. Okay, so the probability of that is going to be 3 out of 4, because I got 4 items within my sample space. Okay, G. The event of getting 2 faces that are the same. Well, that would be a head, head, tail, tail. So the probability of G would be 2 out of 4, or half. Okay, H. The event of getting a head on the first flip, followed by a head or a tail on the second. Okay, so it's got to be a head on the first flip. So there's a head on the first flip. That's a head and then a tail. So we can write that one. And then here's a head on the first, and then head or tail on the second. The reason why I don't choose this one or this one is because this is a tail on the first flip. So the probability of H would be 2 over 4, or half. Okay, then F and G, are they mutually exclusive? So here is F, and here's G. So we're going to look at F and G. Do they share anything in common? Well, it looks like they both have a head, head, and that's it. So because they have something in common, and also we could look at the probability of both of them. This would be 1 over 4. Because this was not 0, and because they do share something in common, they are not mutually exclusive. Okay, I'll let J be the event of getting all tails. So J would be just tail, tail. And then H and J. So we'll move those. So now we're looking at J and H, which is right here. We're going to see if they have anything in common. And nope, doesn't look like they do. So the probability of J and H would be 0. So this would be mutually exclusive. Okay, now this is saying, how do we know if 2 things are independent or not? Well, what we can do is we can use conditional probability to see whether it is independent or not. So remember, when you have a given that's conditional probability. So if the given or the conditional probability comes out to the first event, the probability of the first event, okay, then we say that these 2 things are independent from each other. But if they don't come out, so these 2 things signify independence. If we had the probability of G given H did not come out to just the probability of G, or the probability of H given G did not come out to the probability of H, this signifies dependent events. So if we look at probability of G is 0.6, H is 0.5, and G and H is 0.3. If we look at that right there, and we're trying to see if G and H are independent. So we're going to put this through the conditional formula. Remember, this is the formula for conditional probability, this right here. So the probability of G and H, they said is 0.3. And then the probability of H, because remember, the bottom goes on last. Probability of H is 0.5. When I divide these two, that gives me 0.6, which up here, that's the same thing as probability of G. So the probability of conditional came out to just the first event, probability of G. So therefore, G and H are independent of each other. Now, if we look at this one, I'm just going to look at the numbers they gave me right here. That's all I'm going to look at. Are C and D independent? Well, we can put it through the conditional formula. So if we look at the probability of C given D, that'd be the probability of C and D divided by the probability of last, goes on bottom, so probability of D. So both of them, they give us, that is 0.225. Probability of D, they give us 0.3. That's 0.75, which up here, 0.75, that's the same thing as the probability of C. So we just said that this is equal to this right here. Notice the first event is C, which we got to equal just the probability of C. So therefore, these two things are independent. So yes. And you could have used the other, D given C. So probability of C and D divided by the probability of C. So this would be 0.225 divided by 0.75? 0.3, which this is the same thing as probability of D. So we got to equal to just the very first event. Are C and D mutually exclusive? Well, if we look at this right here, remember the probability of something and something, if it equals 0, then it's mutually exclusive. Since the probability of something and something doesn't equal 0, that means that no, they are not mutually exclusive. They have something in common. Or the fact that this is not 0, it's an actual number, you can say no, they are not mutually exclusive. And then C, what is D given C? Probability of D given C. Which you could go through this step right here, but once we said, yeah, they are independent, we already know that this is really just the probability of D, which they say up here is 0.3. Okay, conditional probability. We've already said that this is the formula for it. Two things, if they are independent, the occurrence of one does not affect the occurrence of another. So therefore, if they are independent, then this reduces down to just this right here. And it's going to be the probability of whatever the first event is. That's what will go right here. If they are independent events. If they're dependent, well then we're going to stick to this formula right here. So like this one. If on a test you had 2 questions, that'd be a terrible test. Number 1 would be true, false, and the second one would be multiple choice with 5 options. What's the probability of getting the second question right, given that you've got the first question right? And let's just say that these 2 questions have nothing to do with each other. Okay, they're completely different from each other. So this is saying, what's the probability of getting the second question, given that you've got the first question? And we just said that one doesn't affect the other. So really, we're just looking for the probability of getting the second question right, which is a multiple choice with 5 options. Okay, so out of 5 options, how many are correct? Well, just 1, and that's it. What is the probability of selecting a person who is not guilty, given that we selected someone who is guilty? Okay, so this is talking about 2 different people here. I've got a pool of people, and go ahead and count how many people we have. So 11 plus 72 plus 85 plus 9 gives us 177. Okay, so out of this pool of 177 people, they're saying that we have already selected someone who is guilty and taken them out of the pile. So the probability of getting someone who is not guilty, given that we have already taken a different person out who is guilty, so that leaves us with only 176 people. And then all we have to do is figure out how many people are not guilty. Well, that's adding up this row right here, and that is 94. So this would be 94 over 176. Okay, this is a dependent